An array is the simplest structure there is. Values packed back to back in memory, each reachable by index in one address calculation. That ON random access is its whole advantage. And four classic algorithms each turn it into something more powerful. Binary search, the two-pointer sweep, the sliding window maximum, and the prefix sum. If the array is sorted, you never have to scan it. Keep a window of high and low indices that bracket the answer, and probe its middle. One comparison rules out half the window. Smaller means go right, larger means go left, equal means done. Compute the midpoint as low plus high minus low divided by 2, not low plus high divided by 2. The latter can overflow. Searching for 55, probe index 7, 41 too small, so the left half is gone, and low jumps right. Probe again, 70 too large, and high drops left. The third probe lands on 55. 3 looks instead of 15. Every step halved the window. That is O log n, a million elements in about 20 comparisons. The two-pointer sweep also needs a sorted array, but answers a different question. Are there two values that sum to a target? Put one pointer at each end. If the sum is too small, the only way up is to move the low pointer right. If too big, move the high pointer left. Each move rules out a whole set of pairs, so one pass settles it. Target 26. Start at 2 and 33. Sum 35. Too big. So high steps into 28. Still too big. In again to 24. Now 2 plus 24 is 26. Found. The pointers only ever move inward, touching each element at most once. So the whole search is ON, no nested loop. Next, the maximum of every window of width k as it slides across the array. The naive way, rescan each window for ON times k. The fast way keeps a deque of indices whose values are strictly decreasing. So the front is always current window's max. The trick? A smaller element sitting left of a bigger one can never win later, so evict it on site. Here, the window is 3. Each new value evicts any smaller ones from the back of the deque, then joins. Anything that has slid out of the window leaves the front. After that, the front is the window max, read in ON complexity. The maxima fall out as 3, 3, 5, 5, 6, 7. One linear pass over the array. The last pattern trades a little space for instant range queries. Build a prefix array where pi is the running total of everything before index I. That build is ON. Then the sum of any range becomes a single subtraction. Build P left to right. Each cell the previous prefix plus the next array value. Now ask for the sum of all the elements of A between 2 and 5. Instead of adding 4 numbers, we can subtract the elements at 6 and 2 in P. That is 23 minus 4 equals 19. One subtraction regardless of how wide the range is. And in 2D, the same idea gives summed area tables for image filters. These algorithms and patterns are the workhorses of the systems layer. Binary search finds pages, extents, and index keys. The two-pointer sweep matches packet pairs and pairs free blocks in allocators. The sliding window max tracks the RTT in FQ Codal and drives GPU max pooling and SQL window functions. The prefix sum powers CUDA parallel scans, database column aggregates, and summed area tables. Each one is just a clever way to write the array's cheap indexing. Contiguous storage with ON indexing, and 4 ways to make it pay. Order it and binary search in O log n. Walk it from both ends with two pointers in ON. Window it with a monotonic queue for running extremes in ON. Or pre-compute its prefix sum for ON range queries. Same flat block of memory, 4 different shapes of leverage.